In the universe, almost nothing remains still. Planets spin on their axes and orbit stars. Stars spin within galaxies. Galaxies rotate like immense whirlpools of light. Black holes can pull space around them. Even the clouds of gas where worlds are born spin before becoming solar systems. The deepest picture of the cosmos is not that of a static stage, but of an immense machine in motion, where every scale repeats the same question. Why does everything spin? Our starting point is not the planets, but something much more fundamental: falling. Gravity attracts matter. Two objects with mass pull on each other. A cloud of gas contracts. A rock falls toward a planet. A star attracts a comet. But in the real universe, almost nothing falls in exactly a straight line toward the center of gravity. There is always a deviation, a lateral velocity, an initial asymmetry, a small tilt that prevents a perfect fall. That small deviation changes everything. When an object approaches a larger mass with some lateral velocity, it doesn't plunge directly toward the center. Its trajectory curves. If the velocity is too low, it may fall. If it's too high, it may escape. If it's in the right equilibrium, it remains in orbit. An orbit, in essence, is a perpetual fall that never quite reaches the ground. The object falls toward the central body, but its lateral motion causes the ground to curve beneath it before it reaches the ground. In this geometry, orbital motion appears. The moon is not suspended motionless above the Earth. It is constantly falling towards it, but it moves laterally enough to orbit it. The Earth does the same around the Sun. The Sun, in turn, moves around the center of the Milky Way. Rotation and orbit are not decorative accidents, but natural forms of motion under gravity. The physical key is called angular momentum. Simply put, angular momentum measures how much a system rotates. It depends on mass, speed, and distance from the axis of rotation. The farther matter is from the center, and the faster it moves sideways, the greater its angular momentum. What is extraordinary is that, if no external force acts to modify it, this angular momentum is conserved. This law explains phenomena that seem unrelated. A figure skater spins faster when she brings her arms closer to her body. No magical energy appears. Her angular momentum is conserved. By reducing the distance of her arms from the axis of rotation, her rotational speed increases. Something similar happens in space, but on colossal scales. A giant, tenuous, and cold cloud of gas can rotate very slowly. If gravity compresses it, its size decreases. Since angular momentum must be conserved, the cloud rotates faster and faster. This process is essential for the formation of stars and planets. Before a solar system exists, there is usually a molecular cloud, a vast region of interstellar gas and dust. This cloud is not completely still. Its particles move in different directions. There is turbulence, shock waves, gravitational influences from nearby stars, and remnants of ancient stellar explosions. Although the average motion may seem small, there is almost always a net spin. When a region of the cloud begins to collapse under gravity, this spin becomes more significant. Gravity pulls matter toward the center. The cloud contracts. But matter with lateral motion cannot fall directly to the center without losing angular momentum. Because angular momentum is conserved, the cloud flattens. The result is a rotating disk. At the center, a star forms. Around it remains a protoplanetary disk, a flattened structure of gas and dust rotating in the same general direction. Within this disk, planets are born. Small particles collide and stick together. They then form larger grains, rocks, planetesimals, and protoplanets. Each collision redistributes motion, but the entire system conserves its angular momentum. That's why the planets in a system usually orbit in a common plane and in the same general direction. The solar system retains the memory of the original cloud that formed it. The planet's spins also stem from that turbulent past. During their formation, protoplanets are subjected to constant impacts. Each collision contributes mass, energy, and angular momentum. Some impacts accelerate rotation, others tilt it. Still others can reverse or drastically alter it. Earth likely acquired some of its rotation during the accretion stage, and a giant impact with a Mars-sized body would have contributed to the formation of the Moon and redefined the Earth-Moon system. Our planet's current rotation is, in a sense, a dynamic scar from its birth. Other worlds reveal even stranger stories. Venus rotates retrogradely in the opposite direction to most of the planets in the solar system, and it does so with extreme slowness. Uranus rotates almost sideways, with its axis tilted more than 90 degrees relative to its orbit. These oddities suggest giant impacts, complex gravitational interactions, or internal processes capable of altering the original rotation. In each case, the spin didn't disappear. It was transformed. Moons also inherit and modify these movements. Many moons are born from disks around young planets, like miniature solar systems. Others are captured by gravity. Still others are formed from impacts. Over time, gravitational tides can synchronize their rotation. The Moon always shows the same face to Earth because its rotation period matches its orbital period. This doesn't mean it doesn't rotate. It means it rotates exactly once for every orbit around our planet. Tidal synchronization demonstrates that spin evolves. Gravity doesn't just attract, it also deforms. Earth gently stretches the Moon, and the Moon raises tides on Earth. These deformations act as brakes or accelerators. Earth's rotation is slowing very slowly, while the Moon is slowly moving away. Angular momentum isn't lost. It's transferred between Earth's rotation and the Moon's orbit. Even when something seems to slow down, the fundamental rule still holds. Angular momentum is redistributed. The same thing happens on larger scales. Stars spin because they are born from rotating clouds. But during their lives, they can lose some of that rotation through stellar winds and magnetic fields. The Sun, for example, rotates faster at the equator than at the poles because it's not a solid body, but a sphere of plasma. Its spin reveals its fluid, magnetic nature. In more massive or younger stars, rotation can be much faster, to the point of deforming their shape and altering their evolution. When a star dies, the conservation of angular momentum can produce extreme results. If the core of a massive star collapses and forms a neutron star, its radius shrinks dramatically. A star that once measured hundreds of thousands of kilometers can leave behind a remnant only about 20 kilometers in diameter. By conserving angular momentum, this compact core can spin tens, hundreds, or even more than 1,000 times per second. This is how pulsars are born, cosmic beacons that emit beams of radiation and appear to blink with astonishing precision. The same law that explains a figure skater explains a pulsar. The difference lies in the scale and the violence of the process. In one case, a human body pulls its arms closer. In the other, an entire star collapses to the density of an atomic nucleus. Physics, however, retains the same underlying structure. Black holes take this idea to an even more unsettling frontier. A black hole can have mass, electric charge, and rotation. In the real universe, many black holes are expected to rotate because they form from stars that were already rotating or because they absorb matter with angular momentum. When a black hole rotates, it doesn't just spin like an ordinary sphere. Its extreme gravity drags nearby spacetime in a phenomenon known as frame dragging. Around a rotating black hole, the very fabric of space is forced to partially accompany that rotation. Spin, therefore, is not exclusive to solid objects. It can appear in gas clouds, dust disks, stellar plasmas, planetary orbits, collapsed stars, and warped regions of spacetime. At each level, the same question takes a different form, but the answer retains a common core. Matter almost never falls perfectly straight. Lateral motion produces rotation, and angular momentum tends to be preserved. When you look away from the planets and stars, the rotation becomes even more spectacular. Spiral galaxies look like frozen swirls in the darkness. Their luminous arms curve around dense centers. Billions of stars move in immense orbits. Clouds of gas, star clusters, and interstellar dust participate in a dance that takes hundreds of millions of years per revolution. The Milky Way also rotates. The Sun, located in one of its minor arms, orbits the galactic center at a speed of approximately hundreds of kilometers per second. Even so, a complete revolution takes about 230 million years. The last time the Sun occupied a similar position in its galactic orbit, dinosaurs had not yet dominated the Earth. That timescale shows that galactic rotation is unlike any everyday motion. It is slow in appearance, but dizzying in actual speed. Galaxies rotate by the same general principle as planetary systems, albeit with a more complex history. In the early universe, matter was not perfectly uniformly distributed. Tiny density fluctuations grew under gravity. Where there was a little more matter, the gravitational attraction concentrated even more. These regions became halos of dark matter and gas, the future sites of galaxy formation. During this collapse, matter received gravitational torques. A torque is an influence capable of changing angular momentum. In the young universe, regions of matter attracted each other irregularly. They were not perfect spheres. Their shapes, positions, and interactions generated small initial spins. As gas fell toward the centers of these halos, it retained some of this angular momentum and formed disks. This is how many spiral galaxies were born. A galaxy doesn't rotate like a solid disk. In a rigid disk, the outer parts should be moving faster in terms of linear velocity to complete a rotation at the same time as the center. In a galaxy, stars have their own orbits. Rotation depends on the distribution of mass. Based on the amount of visible matter, stars farther from the center should be moving much slower than those in the center, much like Neptune orbits the Sun more slowly than Mercury. But observations revealed something surprising. In many spiral galaxies, the outer stars are moving too fast for the amount of visible matter. Their rotation curves remain almost flat instead of drooping as expected. This anomaly became one of the strongest pieces of evidence for dark matter. Something invisible seems to be providing extra gravity and holding the outer regions of galaxies together. Galactic spin, then, doesn't just show movement. It also reveals an absence. Galaxies rotate in a way that betrays the presence of mass that doesn't emit light. Dark matter isn't directly detected with conventional telescopes because it doesn't shine or absorb radiation in any appreciable way. However, its gravity affects the movement of stars, gas, and entire galaxies. Spin becomes a tool for studying the invisible. This detail introduces a dimension bordering on mystery. Galaxies are visible thanks to their stars, but their rotation seems largely controlled by something unseen. Each orbit of a distant star around the galactic center acts as a clue. If visible matter were the whole story, many galaxies wouldn't move the way they do. The universe seems to have built its luminous swirls within invisible scaffolding. The rotation of galaxies also explains why they have their shapes. In a spiral galaxy, gas can cool and flatten into a disk. Spiral arms form there, not as rigid structures, but as density waves. Stars and gas clouds move in and out of these regions, where matter is compressed and can trigger the birth of new stars. Spiral arms shine because they contain many young, massive, blue stars, but they aren't fixed material arms spinning like fan blades. They are dynamic patterns within a rotating disk. Elliptical galaxies tell a different story. In these galaxies, stars move in more disordered orbits with less disk structure, many formed from mergers of earlier galaxies. When two galaxies collide, their stars rarely collide directly because the distances between them are enormous. But gravity rearranges their orbits, distorts their disks, and can transform spirals into ellipticals. The total angular momentum of the system is conserved, but it is distributed more chaotically. Galactic collisions are slow, majestic, and structurally destructive. When two spiral galaxies approach each other, their disks warp, tidal tails appear, and enormous streams of stars emerge. Gas can be compressed, producing bursts of star formation. Central black holes may even merge. The original spin of each galaxy doesn't disappear. It blends with the orbital motion of the collision and transforms into a new architecture. The Milky Way and Andromeda are headed toward a future merger. Billions of years from now, their current structures will be profoundly altered. Their disks will stretch, intersect, and likely eventually form a larger galaxy with a different rotation and more complex stellar orbits. This future demonstrates that cosmic spin is not eternal in a fixed form. It remains as a physical quantity, but its form changes. Galaxy clusters also contain angular motion, though not always in the form of orderly rotation. Individual galaxies move within clusters under the combined gravity of visible matter, hot gas, and dark matter. The gas within the cluster can exhibit turbulence, waves, and complex motions. At these scales, the universe appears less like a clock and more like a gravitational ocean, teeming with gigantic currents. An inevitable question then arises: if planets rotate, stars rotate, and galaxies rotate, does the entire universe rotate? The known answer is more cautious. Cosmological observations indicate that, on large scales, the universe is approximately homogeneous and isotropic. That is, it looks similar in all directions when averaged over enormous distances. There is no solid evidence of significant global rotation of the observable universe. There may be local rotations everywhere, but that doesn't imply that the entire cosmos has a spin axis. This distinction is important. Everything in the universe does not revolve around a single center. There is no cosmic spinning top with all galaxies orbiting a universal central axis. What exists is a vast number of local systems with their own angular momentum. Planets around stars, stars within galaxies, interacting galaxies, disks around black holes. Spin appears again and again because gravity and the conservation of angular momentum produce it naturally, not because everything depends on an absolute center. The expansion of the universe is not a rotation either. Distant galaxies are moving away because space itself is expanding, not because they are being flung outward from a center into a pre-existing empty space. Expansion operates on a large scale. Rotation dominates in gravitationally bound systems. A galaxy can rotate while the universe expands because internal gravity holds its stars together. A planetary system can maintain its orbits while distant galaxies move away from each other. On small and medium scales, rotation is the driving force. On immense scales, expansion dominates. This coexistence defines the cosmic architecture. Gravity pulls matter together, rotation prevents it all from falling directly to the center, disks form, stars are born, and systems stabilize. Without rotation, the universe would have fewer disks, fewer stable orbits, and probably a very different structural formation history. Rotation also creates usable energy. When gas falls toward a compact object, such as a young star, a white dwarf, a neutron star, or a black hole, it doesn't usually fall in a straight line. It forms an accretion disk. In this disk, the inner regions orbit faster than the outer ones. Internal friction, turbulence, and magnetic fields convert gravitational energy into heat and radiation. Some of the brightest phenomena in the universe arise from matter spinning before it falls. Quasars are an extreme example. At the center of some galaxies, supermassive black holes devour gas through hot accretion disks. The material spins at enormous speeds, heats up, and emits gigantic amounts of energy, potentially fueling relativistic jets that shoot out from regions near the black hole. Paradoxically, one of the darkest objects in physics can ignite some of the brightest beacons in the cosmos thanks to the spin of the matter surrounding it. In young stars, accretion disks are also essential. Matter falls toward the protostar, but some can be expelled in bipolar jets. These jets help eliminate excess angular momentum. Without this mechanism, too much rotation would prevent matter from continuing to accumulate at the center. This reveals a crucial detail. Spin is necessary, but it can also become an obstacle. To form a star, the cloud must lose some of its angular momentum. Nature solves this problem through disks, magnetic fields, winds, and jets. Thus, the universe doesn't just rotate because it conserves motion. It also develops mechanisms to redistribute it. Matter organizes itself when it finds ways to move angular momentum outward and mass inward. This exchange occurs in star formation, in black hole disks, in planetary systems, and in galaxy evolution. Neutron stars are among the most extreme laboratories. They form when the core of a massive star collapses after a supernova. Matter is compressed to unimaginable densities. A teaspoon of neutron star material would have a gigantic mass. In this state, the conservation of angular momentum transforms the core's original rotation into a frenetic spin. Some neutron stars rotate several times per second. Others, known as millisecond pulsars, can complete hundreds of rotations every second. A pulsar emits radiation from regions associated with its magnetic poles. If these poles do not coincide with the rotation axis, the beams sweep through space like the light from a lighthouse. Regular pulses are detected from Earth. This regularity can be so precise that some pulsars rival atomic clocks in stability. However, they are not perfect mechanisms. They can experience small jumps in their rotation, called glitches, probably related to internal changes in their crust and the superdense fluid at their core. The rotation of a neutron star is not a minor detail. It determines its emission, its magnetic field, its evolution, and its capacity to produce extreme phenomena. In magnetars, neutron stars with enormous magnetic fields, rotation and magnetism play a role in X-ray and gamma-ray bursts. In binary systems, a neutron star can steal matter from a companion. This matter arrives with angular momentum, forms a disk, and accelerates the rotation of the compact object. This is how old pulsars are recycled, transforming them into millisecond pulsars. But there is a limit. If a neutron star were to spin too fast, the centrifugal force at its equator could overcome the gravity that holds matter together. The star would begin to lose mass or become extremely deformed. The physics of spin imposes boundaries. No material object can rotate arbitrarily fast without consequences. Black holes present an even deeper limit. A rotating black hole is described by the Kerr solution in general relativity. Its rotation affects the event horizon and creates an outer region called the ergosphere, where spacetime is pulled so intensely that no object can remain completely still relative to distant observers. There, rotation becomes a geometric property of space. In theory, it is possible to extract energy from a rotating black hole. Physical processes associated with the ergosphere and magnetic fields can transform some of the rotational energy into radiation or relativistic jets. This idea is fundamental to understanding some active galactic nuclei where supermassive black holes launch jets of particles to enormous distances. The rotation of the black hole and the disk surrounding it can act as a gravitational power plant. The spin of black holes is also measured indirectly by observing accretion disks and gravitational waves. When two black holes merge, their masses and rotations influence the wave signal that travels through spacetime. Gravitational wave detectors register these signals as minuscule distortions. From these, properties of objects that do not emit light are inferred. Rotation again becomes an invisible signature, detected by its effects. On a smaller scale, planetary rotation also produces profound consequences. The Earth rotates, which is why the day-night cycle exists. Its rotation generates an equatorial bulge, influences atmospheric and oceanic circulation through the Coriolis effect, and contributes to the organization of hurricanes, ocean currents, and weather patterns. Without rotation, Earth's climate would be radically different. One hemisphere could be exposed to solar radiation for much longer periods, and atmospheric dynamics would lose some of their current structure. The Earth's magnetic field is also related to the planet's internal motion. In the outer core, liquid iron conducts electricity and moves by convection, influenced by the Earth's rotation. This geodynamo generates the magnetic field that protects the surface from some of the solar wind. Rotation alone does not create the magnetic field, but it helps organize the internal movements that sustain it. On other worlds, the relationship between rotation, internal composition, and magnetism produces very different results. Jupiter, with its rapid rotation and conductive interior, possesses an enormous magnetic field. Mars, on the other hand, lost its former global magnetic field, which affected the evolution of its atmosphere. Rotation also determines the shape of the giant planets. Jupiter completes a rotation in less than 10 hours, despite its immense size. This rapid rotation flattens it at the poles and bulges its equator. Saturn exhibits a similar effect. On these worlds, the atmosphere organizes itself into bands, currents, and gigantic storms. Jupiter's Great Red Spot is a persistent atmospheric vortex, a storm that reveals how planetary rotation can fuel lasting structures in fluids. Even planetary rings are systems of rotation. Saturn's rings are not solid structures, but countless particles of ice and rock, each orbiting the planet at its own speed. The inner particles move faster than the outer ones. Small moons sculpt gaps and edges through gravitational resonances. The rings appear delicate, but they obey precise orbital dynamics, where each fragment conserves and modifies angular momentum in interaction with its neighbors. Asteroids offer another perspective. Many spin on their own axes, some with irregular shapes. Sunlight can slowly alter an asteroid's rotation through an effect known as warp, caused by the uneven absorption and re-emission of radiation. Over time, an asteroid can accelerate its spin until it fragments or forms a binary system. Here, even light exerts a cumulative influence on rotation. The universe doesn't need massive shocks to change the spin of a small body. Sometimes a tiny amount of pressure acting over millions of years is enough. Comets also rotate, and their rotation can change when they eject jets of gas as they approach the Sun. These jets act as tiny natural propulsion systems. They alter the rotation period, change the orientation of the nucleus, and can contribute to fractures. In small bodies, rotation is a living history, sensitive to light, heat, sublimated ice, and the object's irregular shape. Despite all that is known, cosmic rotation still raises open questions. One of these relates to the alignment of galaxies and large-scale structures. Some studies are investigating possible patterns in the orientation of galaxies or quasars. Standard cosmology expects that, at sufficiently large scales, orientations will be essentially random. However, certain observations have suggested alignments that still require careful analysis, more data, and bias control. If any of these patterns were to prove real and significant, they could offer clues about processes in the early universe or about the formation of the cosmic web. Another question arises in protoplanetary disks. Although the general idea of planet formation is well established, the details remain complex. How exactly dust grains grow into planetesimals, how planets migrate within the disk, how angular momentum is distributed, and why some systems end up orderly while others have inclined or eccentric orbits are all active problems. Spin is at the heart of them all. The mystery of solar and stellar rotation also persists. Stars are not rigid spheres. Their differential rotation, magnetic fields, and activity cycles interact in complex ways. In the Sun, the sunspot cycle is linked to the internal magnetic dynamo, which depends on plasma motion and rotation. In other stars, faster rotations can produce intense magnetic activity, powerful flares, and hostile environments for nearby planets. The relationship between rotation and habitability is a particularly interesting frontier. A planet that rotates too slowly can experience extreme temperature contrasts. One that rotates very quickly can have distinct atmospheric circulation, short days, and complex weather patterns. Tidally locked planets around red dwarfs always show the same face to their star, with a permanent daytime hemisphere and a permanent nighttime hemisphere. For years, these were thought to be uninhabitable worlds, but atmospheric models suggest that, under certain conditions, a sufficiently dense atmosphere could redistribute heat. Rotation, or its relative absence, can determine the climate of distant worlds. Measuring rotation on exoplanets is difficult. Some methods allow it to be inferred from changes in brightness, spectra, or indirect heat maps. As telescopes improve, the rotation of planets outside the solar system could become a key clue to understanding their atmosphere, their formation history, and their potential habitability. Each world would have not only a mass and an orbit, but also its own unique rhythm. Rotation also affects the perception of time in relativity. Near massive, rotating objects, the structure of spacetime changes. The combination of intense gravity and rotation produces effects that don't exist in classical physics. On Earth, these effects are minuscule, but they must be considered in high-precision technologies such as satellite navigation systems, where general and special relativity influence time measurement. In black holes, these effects become extreme. Spin ceases to be a simple mechanical property and becomes a profound distortion of the environment where events occur. The initial question, why does everything rotate, reveals several layers. In the first, everything rotates because almost nothing is born without lateral motion. In the second, everything continues rotating because angular momentum is conserved. In the third, gravity amplifies the rotation by compressing matter. In the fourth, the universe redistributes this rotation through collisions, tides, disks, magnetic fields, winds, and mergers. In the fifth, rotation becomes a tool for detecting the invisible, from dark matter to black holes. But there is also a more philosophical answer, though one anchored in physics. The universe rotates because motion is more natural than absolute rest. Perfect rest would require perfect symmetry, exact conditions, and an absence of disturbances. The real cosmos was born with fluctuations. Every tiny difference mattered. A minute deviation in a gas cloud became a disk. A collision between protoplanets tilted an axis. A galactic merger rearranged billions of stars. A collapsed star multiplied its rotation until it became a radio beacon. Rotation is memory. A planet retains traces of the impacts that formed it. A star retains part of the motion of the cloud that gave rise to it. A galaxy preserves the history of primordial talks, mergers, and dark matter. A black hole preserves, in its rotation, signs of the star that collapsed or the matter it devoured. Each turn is a dynamic inscription of the past. It is also about balance. Without orbital rotation, planets would fall into their stars or escape into space. Without rotating disks, the formation of stars and planets would be less efficient. Without the transfer of angular momentum, many structures could not evolve. Spin is not an ornament of the universe. It is a condition of its architecture. Even so, rotation never acts alone. Gravity pulls inward. Pressure pushes outward. Magnetic fields channel matter. Radiation heats and pushes. Friction transforms energy. Tides slow, synchronize, and warp. The universe spins within a constant negotiation between forces. That negotiation produces everything from the apparent serenity of a planetary orbit to the violence of an accretion disk around a black hole. On a human scale, the planet's spin marks the days. On a lunar scale, it regulates tides and synchronizations. On a solar scale, it accompanies magnetic cycles. On a galactic scale, it reveals invisible matter. On a relativistic scale, it drags spacetime. The same idea runs through everything. When matter moves under gravity and conserves angular momentum, the natural result is rotation. That's why the image of a rotating universe is not only visually powerful, it's physically profound. The swirls of galaxies, Saturn's rings, the orbits of exoplanets, pulsars, and the disks of black holes are all part of the same family of phenomena. They all show that the cosmos doesn't build its structures through stillness, but through organized motion. In every turn of the Earth, in every orbit of the Moon, in every spiral arm of a distant galaxy, the universe repeats a silent rule. Motion doesn't disappear without a cause. It transforms, distributes itself, accelerates, tilts, hides, or becomes visible in luminous structures. Rotation is one of the ways the cosmos preserves its history. And that's why, from the nearest to the farthest reaches, the universe always seems to be rotating.